All right, so with that amuse-bouche, we're going to move on to our first story. And if you have been paying attention to the news, you might have heard about these fast radio bursts, and they popped up in the news about 2 weeks ago. And so USA Today had an article with the title, "Scientists Detect Unexplainable Radio Signal from Outer Space that Repeats Every 16 Days." So that sounds pretty mysterious. The Metro, which is a paper in the UK, talks about these mysterious repeating deep space signals, and they may have even been produced by aliens, an astronomer says. If you 9 News in Denver also did a story, although they also involved a theremin musician as part of the story. So you might want to watch this just for that amusing part. But here, the title of this story is "Fast Radio Burst Detected from 500 million light years away. It's nothing to do with aliens," astrophysicist says. So there's clearly competition between non-alien and alien astronomers. And then finally, the weirdest title that I've seen is from a newspaper in Athens, Ohio. And here they say, "Scientists have detected radio signals from outer space that repeat every 16 days. ACRN's Valentine's Day prom will take place Friday." So if you really wanted to find out about that prom event, you can do that as part of this story as well. All right, so what are these fast radio bursts? Well, it turns out that this is a relatively new phenomenon as astronomy and astrophysics go. And the very first one was detected just over a decade ago in 2007. And it was done at a radio telescope down in Australia called the Parkes telescope. And this is a 64-meter dish, so that's a pretty big telescope. And it was actually discovered, the fast radio burst was discovered serendipitously in the sense that an astronomer, Duncan Lorimer, had asked a graduate student to basically go back and look through some old data that had been collected. And when they went through that data really carefully, they discovered this really strange signal that didn't seem to match any other known astronomical object. And so this is the very first fast radio burst, and it's called the Lorimer burst by people who do research in this. So this is kind of an interesting phase in this particular field in astronomy, in the sense that it's so new that people are still being, these bursts are being named after the person that's responsible for discovering them. And here is what the radio signal looks like. And so at the what we're seeing at the bottom is time, and this is in milliseconds, meaning 1,000th of a second. So 1 second, is from up to here, and this is 1.5 seconds. And this burst takes place over on the order of a few hundred milliseconds. So this is an extremely fast event. And this is what the burst looks like as far as the energy over time. And what it did was that it was actually so energetic that it saturated the detectors, and so the baseline for what the detector understood to be the baseline got completely confused, and so that's why there's this difference between the left and the right side here. And then what we're seeing plotted along the y-axis or the up and down axis is frequency. So the frequency of the radio signal, and so the higher frequencies are up at the top, and the lower frequencies are at the bottom. And so what you're seeing is that at the beginning, so early on in time, you have like around 700 milliseconds, you have the highest frequency signal arriving, and then as you wait longer and longer, you get lower and lower frequency signals. So here we can see that again, frequency over time, and so this is very strange because for radio astronomers who study signals from pulsars and other radio sources, this was very just how quickly the signal was very different than other sources, and the fact that it happened basically just once. So when they went back through the data and when they tried to localize the source, they didn't really find any sources that were like this in the sky. And the situation remained like this for a few years until 2013, when another set of another source was discovered, and so this again was named after the lead author in the paper. So this is known as the Thornton bursts, and so now we have two objects now exhibiting this behavior. So astronomers now think, oh, must be a big population of these objects, and since then they have been proven right. So that right now there has been over 100 different fast radio bursts that have been discovered. And so you can go to this website online called the FRB catalog that details the properties and the locations of the 100 known, actually more than 100 known bursts. In 2014, the first fast radio burst that was not discovered at the Parkes Radio Telescope, it was discovered at the Arecibo dish down in Puerto Rico. And so here is this particular burst. And again, you have this pattern where there's a delay in the signal for the lower frequency bursts. And so this is named after, this is called the Spittler burst, again named after the first author of that paper. And so let's talk about why you would expect for that delay to actually happen. And I think I accidentally repeated these slides. But this is actually not entirely unexpected, and it has to do with how the photons carrying that radio information travel through space, and how they can interact with charged particles like electrons that are in between us and that source. And basically what happens is that if you do have, let's say, a loose smattering of electrons between us and that radio source, the photons will actually interact with those electrons. And their interaction will actually slow down the radio signal. And what would happen is that the more energetic photons, the more energetic radio waves, which are higher frequency, they kind of power through the intervening electrons, whereas the lower frequency and less energetic photons will interact more, and so they get slowed down. And so what happens is that the more powerful radio photons won't get delayed as much, whereas the lower frequency, less energetic radio waves do get slowed down. And so this actually isn't completely surprising that this happens. Astronomers see this with pulsars all the time. And in fact, you can actually use this to help give you an estimate of how far away the radio source must be. And so astronomers have created theoretical maps of the electron density in our galaxy that would account for what they call the dispersion measure, which is how that radio signal gets changed or how parts of it gets delayed. And so from these maps, they can then estimate how much of a contribution our own Milky Way galaxy must give to delaying those parts of the signal. And so if you look back at that Lorimer burst, that very first fast radio burst, what you find is that given the direction that it's in the sky, the galactic interstellar medium, or the galactic ISM, can only contribute this much, that green band, to the delay in the signal. And then if you, what that means is that the rest of the signal must have been delayed from electrons that are in intergalactic space from our Milky Way to some distant galaxy, and then potentially there might be denser gas with free electrons in that host galaxy that's also delaying the radio signal. And so this is actually a really good clue then that the fast radio bursts are not originating in our own galaxy, but they must be originating in a more distant galaxy, just from this dispersion, the fact that there is this delay. And so here is a video where the person who made the video has collected all these sounds. So if you sonified, whoops, let's do that again. So what we're hearing is basically that delay, where we're hearing the high frequency sounds first, and then as the chirp of the burst continue on, you hear lower and lower frequencies. So let's do that again. So some of them were just barely above the noise, and on some of them, I don't think I could even hear anything, but I guess they, through their analysis, they were able to confirm a burst. And so what you can do is compare the dispersion measure, or the amount of that delay in the radio signals for fast radio bursts, which are in blue up here, compared to pulsars and other known objects in our galaxy that are known to emit radio signals and or also have been observed to have been delayed as well via that dispersion. And what you see is that this line basically separates everything that's inside our galaxy versus everything outside of our galaxy. And then these red diamonds correspond to pulsars and objects in the small and large Magellanic Clouds, which are two nearby satellite galaxies to us. And so you can see that there's really good evidence that these fast radio bursts, none of them are really within our own galaxy, and they are all pretty well outside of our galaxy. And so here is what a basic model of what is happening with these fast radio bursts. The radio signal is coming out. The radio signal has to get through the gas in the host galaxy, and that slows down or disperses that radio signal a little bit. It gets dispersed more as it travels through the intergalactic medium, and finally it gets dispersed a little bit more to get to us as it travels through gas in our own galaxy. Now, what that particular video was actually for this particular burst, FRB 121102, and this was pretty exciting because this was a burst that was found to repeat, and this was one found at Arecibo again. And the reason why having something that repeats is important is that, well, for one thing, you can go back and reobserve it. But the other really exciting thing about repetition is that it tells you what type of models could possibly explain this object. And so we know that there are a lot of objects that are very explosive, like supernovae that go off, but they're a one-time event because that explosion will destroy the source object. But if you have an object that repeats itself, then that means it must not be a cataclysmic event that creates that radio signal. There has to be some kind of longer-lived source to give you those bursts repeatedly. And so part of the problem with discovering these bursts is that the big radio telescopes are still not big enough to allow us to localize or to figure out where these bursts are originating from. And so here we plot the Hubble Deep Field, which is a very famous position in the sky that was imaged by the Hubble telescope for multiple days. And so you can see how many galaxies show up. And then here is kind of the spot in which the irreversible radio telescope will tell you approximately, if the irreversible dish detects a burst, the only thing it can tell you is that that burst will be located somewhere within this field. And if you were able to combine a bunch of radio telescopes together, like the Very Large Array in New Mexico, you can further localize it because those multiple telescopes can give you the resolution of a much bigger telescope. And so you can then be able to tell, roughly where out of all these many potentially tens of thousands of galaxies where that burst is originating, or which galaxy. And so astronomers created dedicated campaigns to try and localize these bursts, and so and they focused on this repeater, and so they used the VLA. They used a European network of telescopes called the European VLBI network. That's that second one, and then as they were getting more and more accurate or more precise locations for that source, they were able to point a ground-based telescope, the Gemini telescope, as well as the Hubble Space Telescope on this source. And what they found was that it was located in a very faint galaxy, and it's not very exciting in the sense that it looks extremely dim, so it's about 100 million times fainter than what we can see. And given how far away it is, it's also smaller than the Milky Way if you were to put the Milky Way at the location of where it is. But because it's so far away, it's emitting a huge amount of light and energy to get to us. And so we think that the emission outshines the entire galaxy when it's bursting. But the galaxy itself is about 1,000 times less massive than our Milky Way. So, that puts a really interesting constraint that a small galaxy that isn't very large and doesn't seem to have much going for it could contain this really strange phenomenon. And they weren't able to find X-rays, and the amount of light that they could see was in the infrared wasn't very much, and so but it does seem like the burst is located in a star-forming region. So here's the central galaxy, and they detect infrared emission coming from warm gas that's been heated up by young stars. So that's also really interesting that it appears in a star-forming region. So whatever is causing this has to do with young stars or stars that die relatively young. And then what's also interesting is that when they did more and more observations and were able to record more bursts, they realized that there was really complicated structure in this. And so I think we're going to hear this. Let's see if I can play this. So it's not just a straight decline, but there seems to be scatter, meaning the signal seems to be extended a long time at different frequencies. And so whatever is causing this, when astronomers create their theoretical models, they'll have to explain these types of signals. So far, we've found basically 4 fast radio bursts up until last year that are repeating or that have been localized. And so one of them is the one that we've been seeing, and then there are these other ones that have been discovered, and you can see that again, none of these galaxies, because they're so far away, are very appealing. But that all changed with a recent experiment that came online. And this is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. And this is a radio telescope that is built in British Columbia, so it's about 30 miles north of the U.S.-Canadian border. And it basically consists of these half pipes that are about a football field in length. And instead of having the dish move to track the sky, it's stationary. And what happens is that CHIME will actually map a large portion of the sky simultaneously. And then as the sky moves, as the sky rises and sets overhead, it will actually see fast radio bursts as they are occurring. And so this is a really interesting way to find objects like this. And so this is exciting because, I mean, it's still looking at a small fraction of the sky, only 0.5% at any given time, but that's still enormously larger than all the other radio telescopes. And through time, they found more than 10 repeaters. And what's exciting is that this particular repeater, FRB 180916, appears to be relatively close by. And so what they did was the CHIME folks worked with the European VLBI network, and they were able to localize the source of that particular fast radio burst. And so we're seeing how big the moon is compared to the size of the location. So initially, CHIME told us that it was within this patch of sky. And if you look in this patch of sky, there's lots of stars and galaxies. But with the network of radio dishes, they were able to zoom in and localize it some more until they found that it came from this particular region in this spiral galaxy. And so this is very similar to the spiral galaxies that we saw earlier that were much closer that we saw with the Hubble Space Telescope. And what is really interesting is that this region here, this kind of triangular spot, through telescopic spectroscopy, they were able to figure this out as a star-forming region. And then what's also really interesting is that it's even in the shape of an arrow that points you to the spot where the FRB is. And so that gives us now a repeater that is in, again, close to a star-forming region. And it's relatively close by, only 500 million or 500 million light years away. And it's also very different from the other ones. So whereas the other galaxies were relatively small and not, they had some star formation, but they weren't spirals. This is one that's more photogenic, and you can be sure that astronomers will be doing a lot of follow-up with this fast radio burst. Now, here is a summary of what we know about fast radio bursts based on the last 13 years of observations and theoretical work. And based on the statistics that we have so far from CHIME and other observatories, there are actually fast radio bursts going off in the sky extremely frequently, as frequent as once every 10 seconds. But because for the most part, radio telescopes weren't pointed exactly at the locations of the fast radio bursts, we didn't really see them until recently. And so with CHIME, with telescopes that can cover large areas of the sky at once, we can now detect more of them. And it's thought that within this next year, instead of having 100 fast radio bursts, we could have 1,000 known fast radio bursts detected. These fast radio bursts are extremely fast, so they basically happen on the order of milliseconds, 100 times faster than a blink of an eye. And they are found in distant galaxies, so they're really not found close by or within our own galaxy. So they must be rare enough that they don't occur, we haven't observed them in our galaxy, but if we expand our sample to cover enough distant galaxies, we find them. And what's crazy about them is that they emit immense amounts of energy, as much as the amount of energy that the sun emits in one day. And so this brings us to the more recent news that came out 2 weeks ago, and it had to do with periodic bursts that appear not only to repeat, but it happens on a regular time scale. And so this is the paper that was released. It was posted to a paper server It hasn't been completely peer-reviewed yet, but the authors wanted the astronomical community to know about it. And so this is, it's actually that FRB 1806 burst that was detected last year from CHIME. And so this is their statistical analysis of the periodicity, and what they find is there's this period at the 16-day mark, and so on average, the bursts are coming over 16 and roughly a third of a day. But what happens is that it doesn't happen right at the 16-day mark. It actually occurs over a period of about 4 days, so plus or minus 2 days on either side of the middle of that 16.3-day period, and the bursts will repeat themselves once every 1 to 2 times per hour. And then after that 4-day window, then the bursts are silent for 12 days. So that's a really strange phenomenon, and this having something like this, again, this is very unlike anything that we've seen in astronomy, and will definitely keep the theorists busy. And even without this, theorists have been kept really busy by just coming up with all sorts of crazy ideas about what could lead to these bursts. And so for a long time, there are ideas involving objects that are within our galaxy, including SETI, aliens being involved. But now we think that a whole host of other models are more likely because these appear to be extragalactic objects. And there's even a website called FRB catalog.org where you can go and see all the different theories, now at least 50 different distinct theories that have been published by astronomers who are trying to explain fast radio bursts. And obviously, most of these have been published before this most recent result. And so I'm guessing, even without having gone through and looked through the site, that none of these theories will match the observations that were announced recently. And so astronomers will be kept really busy to try and figure out why these fast radio bursts are occurring and what mechanism causes or creates the observations that we see. And then finally, as I said earlier, we expect hundreds of fast radio bursts to be discovered each year, and it's not just CHIME and the Parkes Radio Telescope and Arecibo, but there are lots of observatories out there that astronomers are using to find out, to learn more about these. And so this is an exciting time for people who are in this particular field because it's rare in astronomy to find something completely new and unknown to astronomy, and so bizarre that the theorists have trouble explaining it. And so I think for the next 5-10 years, as we get more data, more observations, and those observations will call a lot of the crazy theories out there, and then hopefully over time we'll narrow down and really figure out what could be causing these radio bursts.